plane carrying the device flies over the drop zone. The device is ejected out of the bomb bay doors. It now accelerates as it falls until it reaches terminal velocity. Now, while it's falling towards its target, let's take a look inside. Bob the pilot can operate the exit hatch like so. He stands atop a spring which will compress to lessen the force of the impact, as it will increase the time over which his deceleration takes place, hence reducing the impulse of the collision with the water. The retractable propeller will allow Bob to maneuver the craft once it is in the water. Oxygen tanks hold Bob's breathing supply and are also attached to nozzles that are directed downwards and can expel gas like so. This will aerate the water on impact and so reduce its density. This will mean reduced deceleration on impact. The streamlined exterior of the vessel will cut into the water with minimum displacement of the fluid. This means it will sink further into the water and also increase the time over which the impact takes place. Once again, this will decrease the impulse of the collision, i.e. it's way safer to belly flop than to pencil dive, as you don't sink as deep into the water. Okay, let's zoom out and watch these systems in operation. We will zoom in for a close-up just before entry to see how the impact is dissipated. Gas expulsion initiated. The spring lessens the force. Eventually, the craft slows and returns to the surface as it's buoyant because of the pocket of oxygen inside it. Now Bob engages the propeller and makes his way to land.
The only other mechanism that I could find that seems to work on a similar concept is described in the following video.
In order for the car to stop, all that energy has to go somewhere. If the brakes do the stopping, they dissipate the energy by heating up. Or in the case of a collision, energy is dissipated by the bending and crumpling of metal in the outer areas of the car. And just like how smooth braking is nicer than a quick, jerky stop, cars are carefully designed to crumple when they crash, in a way that lengthens the duration of the impact so that stopping requires less intense acceleration. Lots of acceleration over a very short time is not good for soft human brains and organs. However, people don't like driving cars with Pinocchio-length noses, so most cars only have around 50 centimeters of crushable space in which to dissipate the energy equivalent of our falling stegosaur. That means that while crumpling, they need to maintain a resistive force of about a quarter of the thrust of the Space Shuttle main engine. Over half of the controlled crumpling work is done by a pair of steel rails connecting the front bumper to the body, which bend and deform to absorb energy and slow the car. Most, and in ideal circumstances all, of the rest of the energy is absorbed by the deformation of other pieces of structural metal throughout the front of the car. This meticulously engineered destruction allows a crashing car to decelerate at a high but reasonable and constant rate, just slightly over the acceleration experienced by fighter pilots or astronauts in centrifuge training. As comparison, if cars were super rigid like they were before the 1950s and didn't crumple, they would stop so fast that they would undergo acceleration 15 times what fighter pilots experience in training.